As promised, our next lecture here is looking at why the oceans are the way they are, how they formed, and we'll start by looking at the history of how that was figured out. So we'll get the PowerPoint up here. Origins of the ocean basins. Our best model on how this works is the theory of plate tectonics. It's the prime unifying theory for the geology of the Earth, although we don't see evidence that plate tectonics has operated in the same way for other planets in our solar system. Basic ideas here: the Earth's surface is broken up into many individual pieces called plates, which can move around both vertically, isostasy types of things, but also sideways around on the globe. This provides a very good explanation of the major features of Earth's surface, things like mountain ranges, valleys, continents versus land, all those things we were looking at on the seafloor, like the mid-ocean ridges and the deep basins and things like that. Not just the way they are today, but also going back through Earth history. Where did this idea come from? Well, pretty much as soon as people had decent maps of the coastlines of continents, they noticed that some continent edges looked like they would match up in shape. If you take a look at a world map, you're likely to notice at least a couple places where things would seem to fit together. Probably the best large-scale example, if you haven't spotted it already, would be that South America would fit nicely up against Africa. But say if you looked at the other side of Africa, Madagascar could fit up against there pretty well. Arabia, relative to Africa, swinging that around, would fit in. If your globe shows it, it's south coast of Australia and Antarctica. So there are a variety of places like that. Okay, oh, that's weird. But there was no explanation of why this might be the case. And so it was basically just a curiosity until the early 1900s. Here's an example, somebody drawing a map of squishing the continents together, but okay, they seem to fit. That's all, and as you can see, the maps, a little funny looking. The key figure in initially popularizing the idea was Alfred Wegener, and his model is known as continental drift. This was based on not just the fit of the continents, but by the early 1900s, Wegener had additional information. Fossils had been found on different continents that matched up across the continents rather than with their present positions, and also other geologic features, types of rocks and structures where you have mountain chains, things like that. Now, of course, there's a lot more data today than we had early 1900s, but it was beginning to have some. Wegener actually was professionally a meteorologist, and he did quite a lot of work in Greenland. They certainly have weather there. Wegener, based on these lines of evidence, proposed that all the continents have been attached together in supercontinent of Pangea, Pan, all, Gea, Earth, and ocean around them, Pan, Thalassa, Thalassa is ocean. Pangea then breaks up, and the continents drift to their present locations. In his model, the continents moved along, plowing through the seafloor. He had the continents joined together for most of the time when we have common fossils, known as the Phanerozoic, and being pretty extensively connected all the way up into the beginning of our latest ice ages. So these maps are how Wegener envisioned things being. Unfortunately for the acceptance idea, he was wrong on a number of counts. We now have much more evidence supporting the basic idea that the continents were all joined together and have moved to their present positions. But continents can't plow through the seafloor. This is a big problem for geologists accepting the idea. They remember, which rock is denser? It's the seafloor rock. If you're forcing them together, seafloor is going to win. The denser rock, not the less dense. So continents cannot plow through the seafloor. Turns out he also had the continents joining together too soon and breaking up too late. And so people looking at the early or late end of when he was proposing that things were connected, no, it didn't seem to match up as well. So he had some problems there. Another thing was that Wegener was an outsider. Already mentioned, he was meteorologist rather than geologist professionally, although obviously to come up with these ideas, he studied a lot in geology. There was also the political aspect. Alfred Wegener, as you might guess, he's from Germany. And Germany is not the most popular place with other parts of the world in the 19 teens. You've got World War I and afterwards. And so the response in, say, United States or Soviet Union tended to be along the lines of, no way, he's nuts. What's this German meteorologist trying to tell geologist stuff? Europe response was more moderate. You had some folks saying, nah, or, well, he's got some good points, but there are problems. Part of this, Europe is made up of smaller countries than the US or Soviet Union. And so if you're studying your rocks, working your way along, and then, oh, I didn't bring my passport, I can't go look at those rocks, but I can read books published by the folks over on the other side of the border, and, well, yeah, they know what they're doing. They get geology that matches what we see over here as well. So being in Europe, folks tended not be quite so quick to reject somebody just because they were from the wrong country. Also, Southern Hemisphere, there tended to be somewhat more evidence there, and so geologists working there were often more receptive, notably Alexander Dutoit from South Africa. As it turns out, what are now the southern continents were joined up together sooner and broke up later than the northern ones. So folks there did have more evidence they were looking at than the folks working in Europe or North America. Dutoit had additional information on the fossil distributions, in particular from South Africa, and studied the rocks there quite a bit. Did some schooling in Europe as well, but mostly in South Africa. And he also was able to get a grant to go over to South America, study the rocks there, and find quite a few similarities to the ones that he was familiar with from Africa. Again, geologic layers, mountain belts, folds, faults, things like that. He was able to find matches between Africa and South America. There are even some living organisms that are found in places not now connected, where the distribution makes sense if their ancestors lived on continents that were joined up differently than the way things are today. Another thing, looking in rocks, I'm able to find scratches from ancient glaciers and older ice ages, and the directions of the glaciers don't fit with modern day arrangement of the land. Dutoit was among those improving Wigner's model, also in noting that he had things connected too long, and so refining the model somewhat. Here are a couple of examples of key fossils. This leaf here is known as Glossopteris, from a distinctive type of fossil tree. And leaves like these are found in South America, in Africa, India, Antarctica, Australia. Trees are not great swimmers, and so the fact that these leaves are found on these different continents strongly supports past connections of some sort. Another fossil here, this is Mesosaurus, rather small, kind of reptile-y thing, not exactly a true reptile. Although it is a swimmer, it's pretty small, maybe half meter long at the most. Not a great candidate for trying to swim all the way across the Atlantic, and actually seems to have been in primarily freshwater habitats, but it's found in Africa, in South America. Geologic layers. Here we have several different continent areas, and we see quite similar layers with the same symbols found across the region. It'd be quite strange if somehow independently each continent had the same stuff piling up, but if they were all connected, that would make much more sense. The little skeleton here, that's from Mesosaurus again. Geologic features, we see down here, pattern of mountains, faults, other geologic features that match up across the continents if we fit them together. Up here shows glaciers with arrows showing the direction of them. There are two things that are somewhat strange about these. One, you don't particularly find much glaciation, equatorial Africa, middle of India, places like that. But if these once were near one of the poles, that would make a whole lot more sense of why you'd have a glacier there. Also, the directions, particularly for South America and Australia, the direction that the glacial ice was moving to scratch across the rocks and leave the traces that we can see, seems to be coming from out in the ocean. That's a problem because you can't build a glacier on the ocean. The way you make a glacier is for the winter snow to not totally melt in the following summer. And so there's still leftover ice from the old snow when next winter comes along and the new snow falls. And if this keeps happening year to year, eventually the buildup of the packed down snow will create a glacier, and then as more ice piles up, it becomes somewhat squishy, kind of like Earth's asthenosphere, and is able to flow and push its way across the countryside. But if you put snow in the ocean, it does not pile up. We can't make a glacier on the ocean, we need land to build it on. There's no land there, but if the continents moved, we could have land in those places. So here's a more modern diagram of how we understand continents to be arranged during Pangea. And indeed, those areas who are near the South Pole make sense to have glaciers there, matching rocks. Conversely, we also have these areas shown in brown that have extensive coal beds, formed in what were tropical swamps. Pennsylvania, Siberia, Germany, not great places for tropical swamps these days. Once again, if we can move the continents, we could have them be near the equator, making rather more sense. But we're still saying if. How could this happen? Here's a diagram, excuse me, showing the general movement of the continents. But we need a way to have it happen. Starting in the 1940s, in particular, a little bit in the 30s, but mostly 40s through 50s, we had new discoveries that led towards the acceptance of plate tectonics. Basically, in 1960, the idea of moving plates was still kind of on the fringe. By 1970, it was firmly established. So what led to this relatively rapid change in view among geologists? One set of clues comes from the detection of traces of magnetism in rocks. Of course, familiar, the Earth has a magnetic field. We can detect that with a compass. But we have traces from the influence of the magnetic field that we can measure in rocks. And there are some changes in that that can be quite informative. Also, new technologies allowed much greater study of the seafloor. As mentioned, discovering all those features on the ocean floor. A lot of the technology was developed during World War II for military purposes, but once it was available, then able to study things a lot more extensively. Those geodes, the funny flat top undersea mountains, look like they'd been eroded at the top by waves, but here it is way under the ocean surface. How could you get the waves there? Kind of those mid-ocean ridges, again, the variations in density in the layers, evidence for the age of the seafloor, all of these were tying in. Magnetic field, look at that, well, one aspect of that now, and we'll get to others later. Quite familiar, the idea that you can take a compass and use it to measure and figure out which way is north. Something that's much less familiar, since most people don't use it very much, is that it also gives an angle up and down. If you have a compass, you may be able to do this in class, if we can figure out a good way of keeping things sterile. But at any rate, taking a compass, okay, hold it flat, you can figure out which way is north. If you turn it sideways from there, you'll see the needle pointing at a bit of an angle. If you think about this shouldn't be too surprising, because if you were standing at the North Magnetic Pole, the compass needle would be pointing down rather than sideways. And so as you go from the north to the south, you'll go from the north end of the needle pointing down through horizontal all the way to pointing up at the South Magnetic Pole. If a rock is melted, it's magma, or if we have loose pieces of sand and mud, then the magnetic bits within that can jiggle around and move, line up with the Earth's magnetic field, just like the compass needle does. But as the rock solidifies, whether it's cooling from magma or the pieces getting stuck together from sediment, eventually those pieces are no longer able to go around. They'll be stuck lined up with however the Earth's magnetic field is when they form. Now, of course, something important to do, if you have just a loose rock, well, you could measure magnetism in it, but that doesn't help you any, because which way was up, which way was north? You have to get a rock that is still firmly attached to the Earth and either mark the directions, then take it back to the lab, or do measurements out in the field to determine the magnetism here. Now, if our rock moves, say plate tectonics works, or if there's a change in Earth's magnetic field, then the rock magnetism will no longer line up with the Earth. What happens when you do these measurements? Well, here's what was found. If you measure rocks, say in North America, and you look at older and older rocks, where the North Pole seems to have been based on those moves across the globe. And that's a little strange, referred to as apparent polar wander. If you do these types of measurements in Europe, again, you get movement of the pole over time. An even bigger problem is the older things get, the further apart the apparent poles are. Earth being a globe, there's only one North Pole. How can we have poles in different places? Well, if the continents can move, then those tracks line up pretty well. Another piece of evidence, the discovery of the mid-Atlantic ridge. It is around the middle. We saw the Pacific not so much so, but the mid-Atlantic ridge does line up roughly in the middle, about where you might expect to see something if indeed the continents had split apart. But again, how? We didn't really have any way for this to work. And that was a big obstacle to accepting the idea of moving continents. But as things go on through, in especially 50s, 60s, a lot of people are involved, a lot of discoveries, and we have the establishment of the new idea, plate tectonics, significantly improved version from Wegener's model, and overwhelming support. Folks still a little doubtful. By 1970, we had the first of those major ocean drilling ships going out, sampling the ocean floor, and what it found was just what plate tectonics predicted it should. And that really convinced practically all of those who were still hesitating at that point. Yeah, you can still find silly stuff, say, on internet or whatnot, but there's not serious doubt that the continents are moving. You can measure it with GPS today. One of the key figures in this process was Harry Hess. Actually, he failed one of his first geology classes, but became one of the most influential geologists of this past century. Don't recommend you trying to imitate that grade, but seeing what he did achieve. And what he did was really put together lots and lots of different pieces of evidence and putting this into a new model, hence plate tectonics rather than continental drift. Plate tectonic ideas, of course, he's drawing on a lot of other folks have proposed different things, but he really put the evidence and ideas together to give a strong case for things. So here's the title page of one of his most famous papers on this. A photo of him from the Princeton Geology website. And note that's not exactly a geologist outfit. During World War II, he was in the Navy. His job was to keep an eye on the sonar radar, watch out for any evidence of enemy ships or submarines, but also he was keeping an eye on what it told him about the bottom of the ocean. So he got a good deal of information about types of seafloor features, and after the war was able to further build on this and get a good picture of some of what was found under the ocean. Some of the many pieces of evidence that he put together. This is a very good sign for a hypothesis if it draws many seemingly random independent things all together in one single explanation. He estimated that for the deep ocean, way out away from land, there's not too much there, and so only about 1 centimeter of sediment every 1,000 years piles up. If so, then the deep ocean appears to be significantly younger than a lot of the rocks up on land. Likewise, the number of old volcanoes down at the bottom of the deep ocean seem to be less than there should be if the ocean just sat there since the initial creation of the Earth. Those funny flat-topped undersea mountains, one, they tend to be shallower if they are found closer to the mid-ocean ridge, and deeper as you get further out. And those flat tops, when they were sampled, proved to have fossils from shallow water settings like reef corals of shallow water types and the like on them. The mid-ocean ridges, we've already mentioned their location. A few other unusual features of them. They're areas with high levels of heat coming from the interior of the Earth. Earthquake waves go somewhat slow through the mid-ocean ridges, telling us there's something different under there. That Rift Valley system we mentioned, a lot of volcanism. Now it's typically pretty calm, just kind of crack and a bit of lava oozes out and cools into a lump of basalt rather than being more explosive, but it's very common. Also, there's trenches. There's somewhat lower gravity associated, not just what's explained by it's water, not rock. There's some less dense rock associated with the trenches. What's going on with all of these? So Hess proposed the idea of seafloor spreading. Now, there had been some previous suggestions along this line, but Hess really put the data together to support it. Basic idea, this is his sketch of it. We have areas where hotter rock, being less dense, rises up, reaches near the surface, moves out to the side, cools down, eventually sinks. And so we have these large-scale cycles, loops of hotter stuff rising, things moving out, cooler stuff sinking down. Same sort of thing happens, say, if you heat a pot of water on the stove. Stove's heating the bottom of the pot. Water at the top gets hot too. How's that happening? The main thing is that the water on the bottom gets hot, becomes less dense, so it'll tend to rise. The cooler water at the top of the pot sinks down. Now it's closer to the burner, it gets hot, and so you get this cycling happening. It happens in the air as well, very important process in meteorology. No surprise, rock, much slower, but it is happening. We can now detect it looking at earthquake waves. Where we have the sinking down happening, say over here, the less dense rock from the surface are being carried down into the interior of the rock, happening at the trench, sorry, interior of the earth, at the trench. So less dense rock sinking down, surrounded by some more denser stuff, that gives us the lower gravity there. Also, this old seafloor is sinking down. That's why the seafloor doesn't look as old. All the old stuff's gone. It's been squished down at the trenches, apart from tiny bits here and there that got stuck and are preserved in random places. Here's a more modern picture. We've got color printing rather nicer these days than back in '62. And so we have the idea, a diagram cutting down into the earth, cross section here, hotter mantle rock rising up under the mid-ocean ridge, moves out to the side, cools, sinks, and we have that circulation going on. Hot rock rising up. Well, the ridge sticks up. It's higher because of the hot material under. That will also explain why there's high heat from Earth's interior. This is a place where hot rock's rising. Hot rock, less dense. Earthquakes go slower. It's explaining that. If the two sides are pulling apart at the mid-ocean ridge, that crack in the middle, that's where we'll have our rift valley. This is explaining a lot of different things. At the trench, stuff's sinking down. We're trying to shove one plate under another. That's a rough process. We're getting earthquakes. As it sinks down, gets warm, melting, we get the volcanoes. Hot rock rising, less pressure, it can melt. We get the volcanism with the mid-ocean ridges. Cracks moving apart, not quite as bad as colliding, but still we get earthquakes there. So again, this is explaining quite a lot of things. As the warm, newly made ocean floor is pushed on out to the sides while new stuff comes up behind it, it's going to cool. As it cools, it's going to get denser, sinks down, isostasy. This is why what was an island closer to the ridge, as it moves on out, sinks. And eventually is no longer an island, but becomes a geo. Further study confirmed that indeed the seafloor is moving apart at the mid-ocean ridges, and new ocean crust is being built there. One rather impressive example of that, there was a study being done, had a little station with some devices to measure what was going on. This was attached to an anchor near a bit of mid-ocean ridge off the coast of Washington State, some of the closest places to mainland of the US where you can get to that sort of thing. It was set up so there was a float on top, and go out with your boat, send a radio signal down, and the anchor would let go, and the instruments would float up to the surface, and then scientists could pick them up and get the measurements. Based on things like earthquake waves, they could tell that something interesting had happened there, and so went out to get their instruments, get data from close up, sent the radio signal, and nothing floated up. What's gone wrong here? Eventually, they had to send a submersible down to check it out. Turned out that actually their instruments had been right where there was a volcanic eruption, and the layer of lava had actually covered the anchor and the part of the attachment that was supposed to let go. So they had to cut it free, but once they did, they had their instruments, and that had some quite interesting measurements being so close there. Again, the Rift Valley, that's just what you should see. Where two sides are pulling apart, what's in between should fall down. You've got faults along the sides of the valleys. The bottom of them is made up of fairly fresh basalt from these generally pretty calm volcanic eruptions. Those zigs and zags in the mid-ocean ridges with the transform faults and fracture zones, well, trying to stick a straight line on a round Earth is a little challenging, and so you get these zigs and zags in the system from that. You also get notable mineral deposits with the cracks associated with the mid-ocean ridges. Water can sink down, gets very hot. Very hot tends to promote chemical reactions, so some of the salt in the seawater may react and become a part of surrounding rocks, changing the minerals there. Other things may dissolve in the water and be carried with the water as it trickles its way through, comes back up to the surface as hot springs on the sea floor. This can produce areas of extreme high salinity and high temperature water, and this has a number of important effects. For one thing, some of those minerals dissolved in the water are relatively energy rich and can potentially be used as an energy source by certain types of bacteria. Of course, once you have bacteria, you can have things eating the bacteria and so on up the food chain. So there are distinctive deep sea ecosystems that are associated with the undersea hot springs, bringing up minerals from deeper in the earth. Also, some of these minerals are things quite useful to us. There's actually projects going on right now to try to start directly mining these on the deep ocean floor, and concerns about the environmental impacts of these. But also, over time, plate tectonics can take these places and squish them up somewhere easier to get to, and they can then become quite important sources of valuable minerals. For example, over towards Kings Mountain, you had mining of both gold and barite, and both of these were deposited by hot fluids from this sort of system. Also, historically, much bigger picture, in the Eastern Mediterranean, you have the island of Cyprus. The name sounds somewhat like copper for good reason. They are related. Cyprus has these types of deposits now squished up onto land, and it was a key ancient source of copper. Copper, in turn, is one of the components, along with tin, of bronze. Tin, being found in what's now England, was a major region for Pythias, getting up there. Having a Bronze Age, you need lots of copper. And Cyprus was a key source of that in ancient times. One other thing, getting an area of extremely high salinity water here on the bottom of the ocean, if you have a somewhat enclosed area where these hot springs are coming up, or there are other possible situations like where you have a patch of salt in the ground that reaches the surface, you can get actually a pool of extra salty water underneath the rest of the ocean there. It's apparently quite a strange experience. I've not done it myself, but hearing about and seeing videos, to be down in a submarine and see what looks like a lake under you. Wait a moment, we're in the ocean. How do you get that? Heard about one time where a submarine tried to actually go down into it, but bounced off it instead. It was so salty that the density was enough the submarine couldn't penetrate into it. Where two plates are colliding, one thing's being shoved down deep underneath with ocean plates, that is known as a subduction zone. So this is where we lose old seafloor getting squished back down into the interior of the earth. So we'll have a deep sea trench at the boundary there. One plate is shoving down under another. Eventually, if there's continent plates on both sides, they run into each other. Continents, that's a less dense rock. That's not going to shove down very well. If they can't go down, then the alternative is up. And so our tallest mountain ranges are formed where two continents collide together. Himalayas are our most impressive modern day example. The Appalachians, that you can see if you've got a view to the west from here, are a very much eroded down now, but remnant of an ancient similar collision. If we have ocean plates on both sides, well, those are denser. One of them can go down. We'll have the trench. We've got a pile here of sediment scraped off as the plate goes down underneath, scraping one plate under another. Lots of earthquakes, sometimes very big. Also getting deeper, getting hotter. Eventually some of these rocks melt. And so we get an arc of volcanoes next to the trench. Another good bit of evidence supporting plate tectonics is the pattern of the earthquakes. Wadati, a Japanese geologist, and Benioff, an American one, noticed that this pattern in earthquakes around the trench. And so it's known as the Wadati-Benioff zone. Earthquakes are deeper and deeper down in the earth as you go along from the trench, and it slopes down into the earth. And this is exactly where earthquakes should be if we're shoving one plate down under another, all along that plate. In fact, very deep earthquakes are only found around ocean trenches at the subduction zones. Why would they only be there? Well, what's around the plate? Deeper down, we're underneath our usual plate depth. Plates are made up of the lithosphere, the rigid stuff. Underneath them is the asthenosphere, the squishy zone. Put enough pressure onto asthenosphere, and it squishes. That's not an earthquake. Earthquake is going to be when we have some sort of breaking. That's going to happen only in the rigid part. But here at the trench, we've got plate that's being shoved down deep into the earth. And so that rigid rock from up at the surface is now much deeper than usual, and we can still get earthquakes occurring in it far deeper than is normally the case because all around it's asthenosphere. No surprise, collisions can be quite messy. This is a diagram of where India is shoving into Asia. Southeast Asia corner here is basically stuff shoved aside by that. And we have some cracks spreading, as well as stuff sliding sideways or shoving up on top of each other. All sorts of things going on in this collision zone. Rocks can be folded or broken in these systems. Again, it's a long, slow period of time, so we do get some that bend before breaking. And a variety of different environments. We have holes where sand and mud can pile up. We have volcanic mountains built that can erode. All sorts of things being deposited that will give distinctive layers and features we can detect then geologically afterwards. Pushing together, in addition to the folds and cracks, the faults that are formed, we can actually shove areas of rock up on top of other rock. Again, this is an area where you've got continents, and neither one goes down very well. Instead, it's near horizontal, which is often referred to as thrust faulting going on. So this is a good indication of collision. We have some quite classic, impressive examples of thrust faulting visible here in western North Carolina. For example, we go up to Lindenwold Falls, right near the base of the upper falls. They actually have some signs drawing your attention to it. There's a major fault where one type of rock has been shoved up above the other, and that's part of why you have the falls there, in those different rocks. Again, these continent-continent collisions give us our most massive mountains, like the Himalayas. We don't see much in the way of volcanoes. There's so much continental plate on top there that melted stuff generally doesn't make it all the way through. But there is a fair amount deep down the earth that melts, and so you get big blobs of rock cooling under the mountains that may eventually be exposed by erosion over time if the mountains have that opportunity. Okay, so that's a good spot to pause a bit, and we'll continue with more of the evidence on plate tectonics next time. I want to draw one more thing here to your attention as well, though.
Change the way geologists saw the world, and brought continental drift back to life. Now everybody sings, yeah! You are a brilliant man. Yeah! You are a brilliant, brilliant man. Continental drift, I'll prevent the state continental drift. I'll prevent the state continental drift. I'll prevent the state continental drift. I'll prevent the state.
So that may help you remember Alfred Wegener a bit more there. You may have noticed there were also a couple of pictures of Harry Hess, although they didn't specifically mention his name.